So charged particle experiences both an electric field's force or the force due to an electric field, as well as the force due to a magnetic field in the case that it is in motion. So this particular phenomenon was investigated in detail by a Dutch scientist by name Hendrik Anton Lorentz at the turn of the 19th century. He conducted quite a few experiments and he came to the conclusion that any charged particle in motion not only experiences an electric field but also experiences the force due to a magnetic field. So it experiences a combination of two forces, the force due to an electric field and the force due to a magnetic field. And this combined force is what was mathematically arrived at by Lorentz. And in his honor, we call that force as the Lorentz force. So Lorentz force is represented by F subscript L, is the summation of the electric field force experienced by a charged particle plus the force experienced due to the magnetic field. So if you were to deal with each of these quantities independently, force due to an electric field, we know from our studies in chapter 1 that it's given by Q into electric field. Recall that Coulomb's law stated that the force experienced by two charges Q1 and Q2 is given by 1 by 4 pi epsilon naught Q1 Q2 by the square of the distance between them. And we went on to convert one of the charges into a test charge and the other charge as a source charge, because of which an electric field is generated, and hence we arrived at this equation. So Fe can be vectorially written. If I have to give it vectorial notation, electric field has direction and magnitude, hence the force experienced by a charged particle due to an electric field is given by Q dot vector E. Similarly, what is the magnetic field? What kind of a force does a magnetic field induce or influence a charged particle with? So we briefly discussed about it previously when we were discussing the context of Fleming's left-hand rule. So the force experienced by an electric charge or a charged particle moving with a velocity v in a magnetic field is given by Q into the vectorial product of velocity and the magnitude of the magnetic field. So Fm is equal to Q into V into B, or if you are to remove the vectorial representation, then we represent it as QVB sine theta, where sine theta is the angle between the velocity vector and the magnetic field. So when I combine these two equations, I arrive at this joint equation. If I remove q as the common term, I am left with this is what is known as the Lorentz force. Now Lorentz force is not always the same because it's dependent on several factors over here. If you recall from the previous discussion, we discussed the direction in which the force is felt in the case of an electric field and the direction in which the force is felt in the case of a magnetic field. Now suppose a particle is traveling parallel to the magnetic field. It is traveling parallel or anti-parallel to the magnetic field. Let's say the north pole is here and the south pole is here, and magnetic field is from north pole to south pole. And my electric charge is traveling from the top to the bottom, which means the angle theta between the velocity of the particle and the magnetic field is 0, in which case this particular term completely becomes 0 because the vector product results in a 0 quantity term. So that means the Lorentz force is only equal to the electric force. Similarly, let's say a particle is traveling perpendicular to the direction of the electric field. If it's traveling perpendicular to the direction of the electric field, again this particular term turns out to be 0. Then the Lorentz force is only due to the magnetic field. So these are some special cases or scenarios which play out depending on the relationship between the movement of the particle and the direction of the electric and magnetic fields. So let's quickly spend a minute on trying to arrive at the units for electric field and magnetic field. So electric field, you might already be aware, we already know that E is equal to F by Q, hence we can deduce that the unit for electric field would be newtons per coulomb. Or we have also gone on to use the other unit, which is volts per meter. So this is based on our discussions during drift velocity and the movement of current electricity. Similarly, if I were to look at a magnetic field, so we have the equation magnetic force is equal to QV into B. So I rearrange that equation to give me magnetic field is equal to force divided by Q into velocity. So that leaves me with the units newtons by coulomb, meters per second. So the second term goes to the numerator. So that leaves me with Newton second divided by coulomb meter. Now this particular unit is what we call as Tesla, in honor of Nicholas Tesla, who did a lot of extensive experiments on electricity. But Tesla is too huge a quantity for everyday practical usage. Everyday practical usage requires magnetic fields of much lower magnitudes in strength, and hence we resort to another smaller unit of magnetic field intensity, which is Gauss, again named after a famous scientist who worked on electric fields. And one Gauss is typically about 10 power minus 4 Tesla. So this is a much more ordinarily used unit to measure magnetic field.